As we've already seen in earlier videos, nonmetal elements can join together through covalent bonding, where they share electrons in order to achieve full outer electron shells, making the atoms stable. Sometimes, this kind of bonding leads to the formation of small, distinct molecules such as chlorine or ammonia, which are known as simple molecular substances. In other cases, however, nonmetals form giant covalent structures like diamond, graphite, or silicon dioxide. And in today's video, we'll be exploring the key properties of both types of substances, simple molecular and giant covalent, before focusing in more detail on the structure of silicon dioxide. Now, the first thing you should understand is that covalent bonds themselves are extremely strong, which means breaking the atoms apart that are directly covalently bonded requires a lot of energy. But in the case of simple molecular substances like chlorine, you don't actually break these covalent bonds when the substance melts or boils. Instead, the energy is used to overcome the weak intermolecular forces, the weak attractions between different molecules, which require much less energy to break. Because of this, simple molecular substances tend to have very low melting and boiling points. For instance, chlorine boils at -34 degrees Celsius. And although individual intermolecular forces are weak, larger molecules tend to have more of them, which means a stronger overall attraction. A good example of this is seen in the halogens, chlorine, bromine, and iodine, where, as you move down the group, the atoms and their molecules increase in size, resulting in more intermolecular forces and hence higher melting and boiling points. Bromine, for example, boils at 59 degrees Celsius, while iodine doesn't boil until 184 degrees. While you don't need to memorize these exact numbers, it's important to understand the trend. As molecular size increases, so do melting and boiling points due to the increased number of intermolecular forces. Another key property of simple molecular substances is that they don't conduct electricity, because there are no free electrons or charged particles within the molecules. This is an important recurring concept in chemistry. For a substance to conduct electricity or heat, it must have some free electrons or mobile ions. Moving on to giant covalent structures, these are composed of vast numbers of nonmetal atoms, all interconnected by strong covalent bonds and arranged in regular repeating lattices. This repeating pattern means that the entire structure is held together very tightly. The most significant examples include diamond, graphite, and silicon dioxide. These substances are extremely strong and have very high melting and boiling points, because breaking them involves disrupting a vast number of strong covalent bonds throughout the entire structure. In general, giant covalent structures do not conduct electricity either, as they typically lack any free-moving charged particles, even when molten. However, there is an important exception in the case of graphite, which we cover in more detail in another video, along with diamond. Unlike them, silicon dioxide is made of silicon and oxygen atoms in a 1:2 ratio, and is more commonly known as silica, which is the main component of sand. While you don't need to be able to draw its full structure, you should be able to recognize that it is a giant covalent structure. To summarize, simple molecular substances consist of small, individual molecules made up of a few atoms bonded together by strong covalent bonds, but with only weak forces between the molecules, which makes them easier to melt or boil and also prevents them from conducting electricity. In contrast, giant covalent structures contain a continuous network of atoms bonded by covalent bonds, forming strong, solid lattices with much higher melting and boiling points, and with very limited electrical conductivity. That wraps up everything for now. We hope you enjoyed this explanation, and we'll see you again in the next video.